Respected sir, my name is Yash Kumar Pal, roll number 2K20ME309.
And I am Yash Saini 2K20 ME 310.
We are here to review a research paper on the topic Challenges in the Numerical Analysis of Centrifugal Pumps. Pumps are used in all branches of industry. Centrifugal pumps are developed to operate at a calculation point, but in reality, they operate over a wide range. The service life of a pump and the probability of various damages depend on its operating range. Pumps have a theoretically defined recommended operating range, but it is not always feasible for this condition to be met. From the efficiency point of view, the pump is recommended to operate most of the time near the best efficiency point, that is also known as BEP. For accurate knowledge of the kinematics of the flow conditions in the pumps, the best option is to use computational fluid dynamics, that is CFD. The current article aims to present various problems that arise when using numerical methods in the development phase of centrifugal pumps and reversible pump turbines. The influence of wall roughness on pump operation is presented in the research paper, uh, and this research paper was focused on issues where it is necessary to perform non-usual procedures in the numerical simulations. The first example is related to the instability of HQ characteristics of different types of pumps. A detailed description of the numerical simulation of a reversible pump turbine in pump mode is presented in the numerical analysis. Results presented in this paper are the result of authors' many years of research in the field of centrifugal pump development. Now, let me talk about instability of pump characteristics. Centrifugal pumps operate under different operating conditions depending on the magnitude of the flow Q and the head H. The relationship of the two variables is given by a function known as the HQ characteristic. Theoretically, this function decreases with increasing flow. The shape of the function is influenced by many operating parameters, so it is not trivial to identify possible instabilities in the operation of the pump. By measurements on the model or prototype, it is possible to determine very precisely the shape of the above characteristic. But without detailed measurement of the kinematics, it is not possible to determine the possible causes of unstable areas during pump operation. By using CFD, it is possible to determine the exact characteristic and also predict the causes of the formation of the so-called unstable regions in the HQ characteristic. All numerical analyses are based on the solution of Reynolds average Navier-Stokes system of equations, that is, continuity equation and momentum equation. Now, this figure 2 shows the measurement and numerical analysis result in the case where the pump characteristic has a well defined area of instability. It is an HQ curve in which the black line gives the measurement and the dotted blue line is CFD for steady and the continuous blue line is CFD unsteady. The results of numerical analysis differ considerably if we perform a stationary or non-stationary calculation. A comparison of the results shows that in the case, it is very important to use a non-stationary calculation that predicts the characteristic of the pump with sufficient accuracy, which is also confirmed by the comparison with the measurement results. In the case of efficiency analysis, there is no such pronounced differences between stationary and non-stationary calculations, but a slightly better result can still be observed compared to the results if a non-stationary calculation is used, as you can see in figure 3. Since the numerical and experimental results agree quite well in stationary calculations, such results can mislead us and it is possible to obtain a bad result for HQ characteristic. If the kinematics of the flow at the inlet to the impeller is monitored in parallel, it can roughly determine when non-stationary calculations should be started. Numerical instability. The numerical simulations according to different operating conditions can basically be divided into three main areas. The first area is near the BEP, the two other are at part load and at full load. Large differences can be observed between these three results if continuous monitoring of the efficiency convergence during the calculation is running. Due to the favorable flow conditions at the impeller inlet, the convergence is very stable in the optimal mode, which can be seen well in the upper curve in figure 4. The other two curves represent the operating range at partial and at maximum flows. At partial flows, a small fluctuation in the efficiency of about 2% is observed, and the maximum flows of instability of convergence is more than plus minus 15%. In particular, this must be taken into account when it is necessary to accurately predict numerically the efficiency characteristic in the wider operating range of the pump.
Inlet recirculation. It is the process in which harmful side effects such as vibration, noise, and erosion damage occurs, whose possibility of damage depends upon the various factors like rotation speed, cavitation characteristics, and suction energy levels at the inlet. The wall roughness. The pumps are made of different materials and with different technological processes, which results in surfaces have different roughness values. The first step in numerical analysis of the flow along rough surfaces is to determine which turbulent model enables satisfactory results and how the characteristics of the computational grids affects these results. Cavitation is the phenomena which occurs during the machine operations. Qualitative numerical prediction can predict the position, the size of the area, and the intensity of cavitation. There are no uniform conditions at the pump inlet, and this situation changes greatly over time, which in fact shows that it is not always possible to obtain concretely useful results using stationary calculations. For linking cavitation and roughness, it was found that it is important to consider the thickness of the cavitation area and not only the size of the cavitation clouds. The current article presents some of the problems that arise in the development phase when CFD analysis is used in the design. For accurate instability analysis in pump characteristics, it is recommended to analyze the kinematics of the flow at the pump inlet. Detailed analysis revealed which computational grades are suitable for the numerical simulation of rough surfaces. Instead of the classical roughness parameters, the so-called sand grain equivalent should be considered in CFD analysis. The results showed that the roughness affects the efficiency and the NPSH characteristics of the pump. The comparison of the numerical and the experimental results shows a slight improvement of the results if wall roughness is considered. All the described phenomena are intertwined, so in most cases, consideration and analysis of all the physical phenomena presented in this article should be done during the development of any new centrifugal pump. That's it for the review of this challenges in the analysis of centrifugal pumps. Thank
Thank
you.
you.